right.
Okay, so
I don't need this.
thanks to Dave and to Jeff to jump across the pond and come in from the United States. So when we made up the program for today, picking out people also from the first 4 days, I said this would be the appropriate people in the Collège de France. I mean, Jeff comes from Michigan, Dave comes from Maryland now, he's in Tucson, and he will give us La Banda, Claude, huh?
There.
Okay, so I asked people for some bit unusual title of the talk, so kinetic Claude, quantum Claude, and then Jeff proposed me observations on observation and control. Thank you, Jeff.
Thank you. I should say, as for David, when Norbert asked me, he didn't just ask me to speak, he told me exactly what I had to speak about. So on command, I will not talk about new mathematics. My job is to talk about the Bardos-Rauch paper on control theory, and I am an obedient servant. That's what I'm going to do. And I'll mix in what it's like to spend a life as part of La Bande à Claude. So the first one, a bunch of us have talked about our first meeting with Claude. My first meeting with Claude was interesting because there was no contact. He was referring a paper of mine, and he found an error, and he figured out how to fix it, and he furthermore realized that the methods that I introduced in the paper solved another problem, at least as interesting, from Jacques-Louis Lyons, and we wrote a joint paper. And that was in, I don't know when it was, but I know it was before 1976. So I think that puts me before Olivier Piranot. It's, so I may be number one here. This was all done, it was in a bygone era where we did mathematics on sheets of paper on which we wrote, and we sent them through the mail across the Atlantic, which takes a long time. It was great fun. And a couple of years later, in '76, I was at the Institute for Advanced Study, and Claude was visiting Courant, and I went up for the analysis seminar, which was, at the time, there was hardly any analysis at the Institute for Advanced Study. The analysis seminar at Courant and the mathematical physics seminar at Princeton were the way to find friendly mathematical spirits, and I went up to the analysis seminar, and I sat in the room next to somebody I know and said, oh, which one of these is Claude Bardos? And that's how we met. And in that same year, I asked Jacques-Louis Lyons if I could visit Paris for my sabbatical year coming up in 1978. He said, sure, you should come. Claude Bardos will organize it. And that may frighten you as a prospect, but in fact, he did a very good job organizing it. And at the time, he was at Paris Nord with Olivier. He organized very well and has been one of my best friends ever since, one of the joys of my life and of many our lives. For the Bardos-Rauch theorem, I will start with a really simple example. This is an example that should be in books, but it isn't. And it's a control theory problem that you can solve easily just by thinking hyperbolically cleverly. But it's easy, it's really elementary. So I want to control solutions of the wave equation on an interval. And that'd be an initial condition. I'm going to take initial condition 0. And the control theory is going to be to drive the condition 0 to a desired state at time t, big T on the slide. There's a Dirichlet condition on one side, and on the other side is the control. So you control, you act on the system by a Dirichlet condition on the right-hand boundary of the interval. And the question is, given a final state that you want to get to, can you drive the system to that final state by fiddling with the control on the right? And you could ask, well, where are the final states? Final states are in the standard energy space, the state U. I don't know how I did that. Control. What happened? Oh, yeah, I've gone to the future. So the U has to be H1, one square integral derivative, has to satisfy the Dirichlet condition that's imposed at the left-hand endpoint, and the time derivative is L2, standard finite energy space. And the answer is there's controllability if and only if t is greater than or equal to 2. And a more precise result you can't possibly hope for. And as you'll see, it's rather an easy theorem. It's worthwhile noticing, and this is one of the key observations, is it takes a little while. You can't control right away. And that's in complete contrast to controlling ODEs. If you can control them, you can control them right away. And this is different. PDEs are not ODEs. There are essentially two steps in the solution. The first step is to understand the wave equation a little bit. And here's the understanding. It starts with D'Alembert. If you factor the wave operator, you discover that this combination of derivatives, ut plus ux, satisfies a transport equation. It moves to the right at speed 1. And the other combination of derivatives, this one moves to the left, transport to the left. The other combination of derivatives moves to the right. So the subscript here means the direction it propagates, not the sign between the two terms. So that's D'Alembert's observation that the solutions of the wave equation is made from leftward and rightward moving modes. Dirichlet condition at x equals 0 says the sum of the two is 0. So if you have a leftward moving wave and it arrives at the Dirichlet boundary, then at that boundary, v plus v minus is 0. The rightward move wave that comes out is oppose. So wave comes in, bounces off, reverses its sign, reflection coefficient -1. So you know what happens at the left-hand boundary. Okay? At the right-hand boundary, the sum of the two guys is ut, 2ut, and that's 2g. That's the control. That's what you can do. So if a wave comes into the right, it's the v plus that will come into the right because it's moving to the right. Then v minus is minus v plus, the guy coming in, plus your control. Clearly, with that control, you can make the wave that comes out be whatever you want. You control perfectly in one reflection. Got that? La bande à Claude. It's Brownian motion. They appear when they want to. For about a decade, Claude ran the Département de Maths Appliquées Rue d'Ulm. We lived in a remarkable shack up on the roof, sort of away from everybody else. You had to be clever to find it. And we had a great time there. There's a whole generation of young people, lots of people here were there, lots of us met there, we wrote papers together, we was a very exciting time, and we who experienced it loved it, treasured it, and thanks, Claude, for organizing that too. You may realize I've just given 2 plugs for Claude's administrative abilities. All right, there's a theorem to be proved. It's controllable if and only if t is less than 2. So I will start by showing that if t is too small, less than 2, you can't control. And here's why. If t is less than 2, then it's not enough time for a signal to go across and back, which means that if I look at points here, and I look at the rightward waves that arrive here, this little interval is the gap between 2 and t. A wave that arrives there has bounced once and then gone back to the initial data. Well, no, I can compute its value. It starts here as 0, boom, moves left. The rightward wave is 0. It arrives here. In this little interval, the rightward wave vanishes. Hey, you can't control to an arbitrary state. That shows you can't control if you violate the condition. The proof of controllability is essentially the same, except it works the other way. If I want to get a state here, now I assume t, this upper limit, is bigger than 2, bigger or equal. This is an amazing case where you can treat the equality case at the same time. If I want to get a rightward wave, well, I'll do the leftward wave here. I trace back to the first point on the boundary where this wave hits. And remember, I have a control there. Okay? So at this point, I will choose the control G to arrange the leftward wave to be what I want. Bang. It propagates there, and you've achieved your goal. For the opposite way, I want to get the rightward wave here. I trace back, boom, I hit there. There's nothing coming in. Here I can always, with my control, I can arrange this wave to be what I want. It propagates, it comes there, takes care of the rightward wave, I win. So you can see why I'm fond of this little example. It says, if you understand the 1D wave equation, you can solve this control problem easy. I defy you to find this argument anywhere in the literature. La manda, Claude. That's the team. If you don't know us, well, you can recognize Claude. He was in one of his fine haberdashery stages, and Gilles in fine form. I wish he were in fine form still, and me. We're at Gilles' 60th birthday celebration in Nice, and the photos by Jérôme Lerousseau, one of our colleagues in PD. And yes, I'll send you a copy of the photo. La banda, Claude, which one is this? Oh, yes. This is how we started working on control theory. It reminds me, there's a famous Steve Smale story about lying on the beaches of Rio de Janeiro, which set the mathematical community in the United States back about 10 years because the political powers did not want to fund Steve Smale sitting on the beaches of Rio de Janeiro. But nevertheless, we were sitting on the beach in Corsica, which if you've never done it, you should definitely sit on the beach in Corsica. It's a spectacular place. It was at the Canum in 1982, and Jacques-Louis Lyons came and he asked us what we thought about the controllability problem for the wave equation, because he knew we were hyperbolic people, that we think about the wave equation kind of differently than he does, and maybe we had some insight into this problem. And we were lucky because we had come from it was a time when the so-called Lax-Phillips conjecture and scattering theory was on not everybody's mind, but on a lot of people's minds, and we were all thinking about it, and we had a way of thinking, which was pretty much the way of thinking of that last example. And so the same intuition that motivated the false conjecture of Lax and Phillips motivated us to make a correct prediction of what the right theorem for controllability of the wave equation was. And we, just like Claude has inspired zillions of us to go on the good quests, Jacques-Louis Lyons had inspired us to go on a good quest. And we first treated interior control, which was interesting because the problem of interior control, where the control, instead of being on the boundary, is on the inside. And boundary control is more reasonable because you can influence from the outside easier than you can influence from the inside. So boundary control is the more natural question. And for this problem, interior control turns out to be technically easier, so that what was the easy problem for this method was the hard problem for the other methods, but that's just the way it was. And we treated interior control, and the problem of boundary control, we needed Gilles. Everybody needs Gilles. If you can get Gilles to work on your problems, you've done a good thing. And our paper in 1992 is by far, I mean, not even close, the most cited paper that any of the three of us has written. And the date is deceptive because this paper spent 4 years at the referee. So when you're grousing about bad treatment by a referee, you can bear this one in mind. It's understandable. The paper is really hard to read, and it uses methods that are not typical for the community. And so I understand the problem of the referees. 4 years, it's un peu exagéré, huh? All right, how are we doing? Who knows? So, higher dimensions. So we're finished with proofs. Our theorem dealt with the problem in higher dimensions, where the one-dimensional wave equation is replaced by the multi-dimensional wave equation, which doesn't have a two-line solution like D'Alembert's. There's lots of waves. They go in every direction. And the control, it's not so simple, one side, the other. The way the control theory is described is you have a Dirichlet condition, and the control is constrained to live on a subset of the boundary, which I'll call gamma, the region of control. And the question is, with controls on this subset of the boundary for an interval of time t, can you or can you not drive the zero set to any finite energy state? And the insight that we brought to the problem was the following. It involved rays. Rays, you know what rays are from looking at light reflecting on mirrors. For this equation, rays are straight lines with the agreement that if they arrive at the boundary transversely, they reflect by the law of reflection that you all know. And that has as consequences, you can take waves that arrive nearly tangentially, and they're going to reflect on a convex part of the boundary many, many times. Limits of those will glide along the boundary, yielding what we call gliding rays. Those count, those are good objects. Another class of rays to think about are rays which miss the boundary, and then you can move right next door, and there are ones that just barely touch it. Those are diffractive rays. They barely touch the boundary. Okay? So we have reflected rays, gliding rays, diffractive rays. Got them? The key thing about rays, and this is a theorem, there's many proofs, none of them are really easy, but crucially important that if you give me a ray and you give me a time, I can construct a solution of the wave equation that almost lives on that ray. That it has energy 1, and if you take an epsilon neighborhood of the ray, it has energy less than epsilon outside the epsilon neighborhood for time t. So rays are carriers of nearly localized solutions. And as soon as you think that way, you realize that if you're going to control from gamma, gamma has to be big enough to meet every ray, because there are going to be these waves that are carrying energy, and if they miss gamma, you're not going to see them, you're not going to be able to control them, you can't control. So a necessary condition for control is that your region of control must meet every ray. For the Lax-Phillips conjecture, that was a theorem of Jim Ralston. And it was a very nice proof. We now do it differently, but it's a good theorem. It was his thesis, 1969. And this necessary condition, called geometric control, I regret, for many years it was called the Bel-Air condition, pronounced rapidly Bel-Air. And I thought, my claim to fame, but no, it got replaced. It's now called geometric control, and we have passed into obscurity. So here are 2 examples. This condition does control geometrically. It may or may not be obvious to you because there's lots of rays possible, but it does. And here's one that doesn't. And to show that it doesn't control geometrically, there's a diameter that misses it, and reflecting back and forth is a ray. And this quickly, for a ball, shows you that geometric control for a sphere implies that you must hit every diameter in at least one point, and therefore you must be at least as big as half the sphere. And it's known, and it was known by elementary methods, that this guy does control. So a little bit bigger than a sphere, you can control. And before our result, it was not known if there were any other sets arbitrarily close in size to a half sphere from which you can control, but with our theorem you can show there were others. Once you know this theorem, it's really fun to play. It's like a video game. You draw a set and you say, where can I control it by? You draw rays and you try to figure out who's the obstruction. It's a lot of fun. I would play the game, but we don't have any time. La bande à Claude. Which one is this? Oh, yeah, La Trivale. I always liked La Trivale because in my head as a mathematician it was La Triviale. But there was, we were meeting Claude on a town in La France Profonde. really, really lost in the Larzac. And we drove down. It's not easy to get there. And we arrived in the middle of the night. It was absolutely a moonless. It was like being in the bottom of a cave. And we had no idea where we were. We were sure we were lost, but it's where the dot on the Michelin map said we were supposed to go. So we went there. I got out of the car. I struggled through the bushes. I find myself in the middle of a field. I'm walking on a field. I'm bumping into animals. I'm stepping into excrement. It's very unpleasant. And then I tripped on this tent, kicking Claude in the process, waking him up. He comes out of the tent, and he's happy to see me. I mean, it's Claude. So we're set up. We move into a room that's been reserved to us. We get special treatment. The room was inhabited by a dense population of flies. I mean, it wasn't like there were a lot of flies. It was like there were small spaces between the many flies. But it was a fine place. There were adventures. We had plates set out for lunch, and the horses ate the plates. And Lulu, the shepherd, was unforgettable. I wish I had photos of Lulu, but I don't. He was a kind guy. He was pungent. He had a two-tooth smile, and he spoke in a local dialect that nobody could understand. All right. For control, some rays are better than others. So there are two kinds of rays that aren't any good for control. If you have, what's going on here? Oh, yeah. That's the one. If you have one of these rays that just kisses the boundary, you try to control there, and you imagine you're doing something on the boundary, you're fixing a Dirichlet data, the ray just goes by. It barely sees the boundary. You can't control from a diffractive point. You can't affect the wave. You just don't have enough contact with it. And there's a second kind of wave you have to avoid, which is a subtle phenomenon discovered by Mike Taylor, that if a ray has infinite order contact with an obstacle, it has non-unique continuation as rays, geometrically. And then you might think, well, the wave equation will settle this inconsistency and we'll always pick one or the other. And Mike Taylor solved that too. No, sometimes it goes one way, sometimes it goes the other. You can't use infinite order of contact is a serious constraint. So in our theorem, which this is it, that says you can control from a set if, and then if is going to be a condition that's just a little stronger than geometric control. If omega has at most finite order contact with lines, first hypothesis, and every ray in the domain meets the control region, the interior of the control region, in at least one non-diffractive point. Remember, the diffractive points don't do you any good. And that's the theorem we proved, and I hope that, one, you have a reasonable idea what it says, and you know one example where you can prove it, and I hope, I'm hell with the proof. No proof. And I would just like to, like the others, express my gratitude to all these years together and my appreciation for the warmth and generosity that you've had towards all of us. Happy birthday, Claude.